Right, let's now talk about motors, right? Now, motors are different to generators in that they kind of have like the opposite energy conversion, right? So in a motor, we're going to use electrical energy. So electrical energy is our input, and the output is going to be mechanical energy, right? So we put in mechanical energy earlier, we got out electrical energy. Now we're putting in electrical energy and we're getting out mechanical energy. Right, so how on earth does a motor work? Well, a motor works due to something that we call the motor effect. Okay, so what is the motor effect? Well, the motor effect is this phenomenon where a current carrying conductor, so a conductor, piece of wire, whatever, that has current flowing through it, will experience a force in a magnetic field. Okay, so don't confuse this with electromagnetic induction. With electromagnetic induction, we change the flux, so basically move something within a field, and as a result, current flows. The motor effect is that we cause current to flow with a cell or whatever it is, but we input current, and as a result of that current, in that conductor is going to experience a force, right? And, you know, in our case here, that force is going to cause the armature to rotate, right? So for motors, we have the same sort of idea where the component for a DC motor is going to be the commutator, right? The split ring commutator, right? So the component for the DC motor is going to be the commutator, right? And when we say DC, we're not talking about the output, which is generators, we get direct current out if we've got the commutator. We're actually talking about the input, right? So for a DC motor, the input has to be direct current, okay? And then you can theoretically have an AC motor by having the slip rings, in which case you would have to input AC current, but the design that we use for that in terms of demonstrating these things isn't really practical. It doesn't work out. So AC motors do exist, but not in this sort of design. But yeah, theoretically you could use slip rings and as a result have an AC motor. Okay, so then what we might want to do is to figure out, well, if the current goes in a particular direction, well, how is this thing going to rotate? Well, we know that we deal with conventional current, and we said that conventional current is going to go from positive to negative. Now we know the long side of the cell is the positive, and then the shorter side is the negative, right? So we have current going from positive to negative, and it's going to be going all the way through here. So we're just following the path of the current there. Okay, now in the same way that we had a rule for the generator, we have a rule for the motor, and that's going to be the left-hand motor rule. And what's fantastic about it is it's basically the same thing, it's just your left hand, right? So the thumb is still going to be the force or the thrust or whatever you want to call it. Your index finger is still going to be the magnetic field, and your middle finger is still going to be the current. The only difference is now you are going to use your left hand, right? So whenever you have motion basically and you get out electricity, right hand, that's a generator. But whenever you input electricity and as a result you get motion, well, that's now going to be the left hand, right? So here for the left hand motor rule, we have to do the same thing that we did previously. We've got to look at a particular side, right? So I'm going to pick the green side, right? And then I know that the field goes from north to south, and that green is going away from me. So my middle finger has to point away from me. And then we'll find actually that my thumb is pointing down. So this is going to experience a force going downwards. And then you can repeat the exercise to show that the pink is going to experience a force going upwards. And then this is going to result in anti-clockwise rotation. Okay, so that's how we find the force that the component is experiencing by using this left-hand motor rule. Now, what on earth do we use motors for? Well, motors are used all around us whenever basically we have electricity and we want to get something to move as a result. So think, for example, of a fan, right? A fan, you can almost see the direct correlation with this, where we put in electricity and something goes round and round and round in order to blow air. Right, so that would be a use of a motor, right? And then the other thing that we might just be curious about is, well, how can we increase the thrust that the motor is experiencing? So basically, that force that causes this thing to rotate, how can we increase that? And not surprisingly, it's going to be very similar to the things that allowed us to have a greater EMF. So we can use stronger magnets. Okay, and note, now I'm not explaining this in terms of that EMF equals negative n times the rate of change of flux equation, because this is not electromagnetic induction. This is the motor effect. So we can use stronger magnets, and we can also use a stronger current, right? Stronger, higher current, however you want to put it, right? So if you use 3 or 4 cells instead of just the 1 cell, you'll get a higher current for the same resistance, and so you'll get a greater torque, which is the force of rotation, right? So stronger magnets, stronger current, right? And yes, if we use more loops or more turns in the coil, it is also going to give us a greater force. So same sort of idea. Instead of going back immediately, we're just going to go round and round and round and round and round until we run out of patience or run out of wire, and then we're going to go back. All right, so stronger magnets, stronger current, more loops, and I would say that we do also kind of have the idea that if we use curved magnets, things should go better for us. Okay, for the same reasons as previously. Okay, so those are the ways in which we can increase that twisting force of the motor, the torque. Right.